Continue, so welcome. So next we need to look at some things that just cause confusion. And there's three terms that one of them is not well known, which is inertia, although we use it in everyday language. Then the other two are used very well, mass and weight, and unfortunately they tend to be used inappropriately. So let's try and resolve this. And the first thing is this idea of inertia. We talk about having the inertia. A football team might have the inertia when the game is going their way and it keeps going their way. Or you might lose the inertia if you basically... my dad used to say I suffered from inertia because he could never get me to go to sleep. And once I was asleep, he could never get me to wake up. So inertia is that tendency to want to keep on doing what you're doing. If you're stationary, you want to stay stationary, and if you're moving, you want to keep moving. And that thing about moving, if you're moving, you want to keep moving, is kind of outside our everyday experience, because when we roll things, they stop moving in the end. They don't have to hit something, they just stop moving. And Galileo was the one who was able to look and extract friction from his everyday experience, and he came up with the term inertia and wrote about it and basically in a way defined it. And then along came Newton maybe 50 years later, next generation or so, and Newton codified it. Newton was a great codifier as well as an experimentalist. Galileo was the first person to look with an abstract eye at what's going on. So we have this idea of inertia. What we say is if we have more mass, we have more inertia, which means we have more of a tendency to want to keep on doing what we're doing, which means it's harder to change doing what we're doing, which means that we have less acceleration, because acceleration is changing doing what you're doing. So more inertia, more mass, more inertia, less acceleration. So we say, given that F equals ma, and that was Newton's law, we see that mass acts to reduce the acceleration resulting from a net external force. So if I have a big object with a force acting on it and a little object with a force acting on it, for the same force, I will get a different outcome. This guy will have a little acceleration because it's got a big mass, and this guy will have a big acceleration because it's got a little mass. So the more inertia for a given force, the less acceleration. So that's basically what that's saying. If an object has more mass, it has more reluctance to accelerate. It is said to have more inertia. So a given net external force will cause less acceleration. And this can have interesting consequences. If you're faced with something that has little mass or something which has a lot of mass, and you've got to decide which one of those you're going to run into in your car, you tend to pick the thing with little mass because you can knock it out of the way. Whereas if you go into the tree, good luck. It's going to be a massive situation. So that's inertia. Then let's try and sort out the confusion between weight and mass. And basically, physically, they're just not the same. Physically, your weight is a force, whereas your mass is mass. It's a scalar. Well, let's go down one. Scalar. And this is a vector. So they're not even the same type of mathematical thing. Weight has a direction. It's always downwards, but it's got a direction. If you're in Australia, you're pointing in the opposite direction, even though you think you're pointing downwards. But, you know, it points towards the center of the earth. Whereas mass is just mass. Well, I say just mass. Mass is actually very abstract. Mass is invariant with space. No matter where it is, you have the same amount of mass. You have the same amount of mass in the middle of the sun, you have the same amount of mass in interstellar space, you have the same amount of mass no matter what. Your weight is completely dependent upon where you are. If you're on the surface of the moon, your weight will be 1/6 of what it is here. If you go to, well, you can't go to the surface of Saturn, but if you go to Saturn, your weight will be more than what it is here. It's completely positional dependent. If you go to interstellar space, your weight will be 0. As it will be if you're in the center of the Earth. If you're in the center of the Earth, your weight will be 0. For a very different reason. So, I should say, at the center of the Earth, your net weight will be 0. And it's not surprising that we get confused, because if you go through to the physics lab and you look on the bench, we have a balance. It's actually called a mass balance, but it's a digital machine which gives you the answer in grams, which is a mass. The process of putting something on here is massing, not weighing. It's massing. And yet when you look on here, it says the weight. It says, made by the scientific company, says the weight is 35 grams. And it's just like shameful. It's outrageous that in this day and age they're calling it a weight. You know, and you wonder why people get confused. Of course people get confused. It's just that people who are used to it don't even notice it. It's that thing about once you train, you just don't spot things. It's the intelligent, non-trained person who catches all the mistakes because they're trying to figure stuff out. So when your answer is in kilograms or a derivative of kilograms, you are massing. When your answer is in newtons, you are weighing. And your kilogram answer will never vary, but your weight answer, your newton answer will vary. And it's even more weird than that. If I go into space and you tell me, pick up those 10 chairs. If you say to me here, pick up those 10 chairs, I say, I'm not picking up those 10 chairs. You're going to pull my back out. That's ridiculous. If we were on the moon and you said, pick up those 10 chairs, I would do it quite easily, because those 10 chairs is like picking up 1.5 chairs, because it's 1/6. So lifting things is much easier when there's less pull of gravity. Makes you think you're stronger. Man, I'm Superman when I go to the moon, because I can pick up things that are 10 times heavier. The problem is not all physical phenomena depend upon weight. Many of them depend upon mass. So for example, if I try to rotate something, the ease of starting the rotation and stopping the rotation is mass dependent. So it's just as hard to rotate those 10 chairs on the moon as it is on the Earth. It's no easier. So you're not super strong. You're not super strong at doing this. You're just stronger at holding it. So quite confusing. Quite different outcomes. If I was on the Earth and a big bus was rolling towards me, then I would try and get out of its way, because just the mass times the velocity of that bus would mean that it would crush me. Yeah, just it's rolling along level ground, but it's rolling, and it would push me against the wall and crush me. If I went to the moon, I could not just put my hands out and stop that bus, because that momentum depends upon mass, not weight. I'm no stronger on the moon than I am on Earth. It's just gravity is less. And then to just give you the final little bit, from my perspective, mass is a complete abstraction. If I plot a graph of, say, force versus acceleration. If I get an object and I apply a force to it, and I apply different forces, so I get different accelerations. I will get a graph that looks like that. And if I took a smaller mass and applied, again, my same forces, I would get a graph that looks like that. For a given force, I'd get a bigger acceleration because it's got less mass. And if I took a bigger mass and I applied these forces, I would get a graph that looks like that. And so for me, I realize, oh, the slope of this graph is mass. And that's just weird. If F equals ma and y equals mx plus b, then my slope, which is ironically called m, is the same as my mass. So it's an abstraction on the graph. Now, chemists will point and say, oh, it's how much stuff you have there. And it is, but it's in a way more subtle than that. It's the slope of a force versus acceleration graph. So if you're in kilograms, what is it? Is it a weight or is it a mass? And if you're in newtons, it's a weight. And neither twain shall meet. Unfortunately, in imperial units, they tend to talk about the pound and the pound. So many pounds of force, so many pounds of weight. So many pounds of force, so many pounds of mass. And it really should be the poundo and the pound. But we're so messed up we don't even bother with that. What we say is, we'll just talk about it in terms of pounds because we're never going to leave. We're never going to leave Earth anyway. You know, which is... Okay. So next we say, all right, let's just take into account two situations. I want to imagine an object, and I'm going to apply different forces. And let's say I apply these forces nice and symmetrically. Then what I find is the sum of the forces in any direction, axis, equals 0. Let's pick an axis. I can say there's that component, and there's that component, and then there's that component, and these guys cancel each other. So there's no net force, so there's no acceleration. That's equilibrium. I've not said if I am moving. I could be stationary. I could be traveling at 1,000,000 miles an hour. As long as I stay traveling at 1,000,000 miles an hour in that one direction, I don't have any acceleration, so I am in equilibrium. Equilibrium is not the lack of motion, it's the lack of acceleration. If I take the same block and I pick a direction, I can say, well, there's one component, there's another component, and even this is a component, and all these point in the same direction, or they have an overall effect. Then I am in a non-equilibrium. That object must accelerate. It's got no choice. So we divide the world up into equilibrium and non-equilibrium. And for equilibrium, we say the sum of the forces equals 0. And for non-equilibrium, the sum of the forces equals ma. These are net external forces in both cases. And also, what's not said so often, but we started with everything in a straight line. It's in a direction. We have to have an axis. We can't just take a force over here and a force over there and an acceleration there and put them in the same equation. We've got to have an axis that we're going to deal with. And that leads us to static and dynamics. And we're going to start off with statics, and we'll do a fair bit of statics. There's a dynamics problem here. I'm going to leave it until next time. We're just going to do statics to begin with. So statics is not moving. Statics is not accelerating. Now, we can give examples where it's not moving. That's where we tend to begin. But don't think that statics is only stationary. It's not accelerating. And the traffic, there's several classic cases. There's the so-called traffic light problem, where we have a mast that's hanging and is supported by a couple of wires. And then we have an object that's stationary on a slope. And then we have an object that's sliding at a constant speed on a slope. They're all statics. And the nice thing is we tend to look at the same problem, so it's a common language that you develop. I'm going to show you several methods of doing this. 2 using trig, 1 using just diagram. First thing, I am not going to give you a nice diagram. I'm going to give you stuff where everything's at 45 degrees, everything's the same length. So don't use my diagram. And my advice when you first begin is get your little protractor and draw this thing reasonably well. Make 30 degrees look like 30 degrees, make 20 degrees look like 20. It will help you tremendously. A poor diagram is a hindrance. When you get practiced, you can kind of guesstimate it with your eye. But initially, just be careful. So I'm going to draw this again. I know the weight, by the way. I know that because G is 10 newtons per kilogram, I know that this is 30 newtons. Yeah, I know that. And I'm going to draw a nice horizontal line and a nice vertical line. And I'm going to draw this at 30. I'm going to be sure it's not 45, so I'm going to draw this at 30. And that's T right. And then this is, well, more like 45. It's more like that, and that's 40 degrees. And that's T left. So there's my visualization to begin with. Nice and big. That's the knot that's in equilibrium, as far as I'm concerned. That's the thing that all these forces are acting on. When something is in equilibrium, I can summarize my forces and say the sum of the forces equals 0 in any direction I like. The obvious choices are horizontal and vertical. Oh, so let me get to that for a minute. How many unknowns do I have in my problem? 2, T right and T left. I want to solve for T left. What's that old adage you learned in math about 5 equations? How many unknowns? If you have 5 unknowns, you need 5 equations. I said it backwards. If you have 5 unknowns, you need 5 equations. If you have 3 unknowns, you need 3 equations. If you have 2 unknowns, you need 2 equations. Yeah. So this is simultaneous equations. Or substitution. It's fancily called simultaneous equations, but it's substitution. Okay, well, let's get on with it. So we're going to change colour of ink so that I'm thinking horizontally. So I look at this and I go, well, that's got a component. Remember your component is always shorter than the original vector. And that's got a component. And I've practiced enough that I can even say, oh, this is going to be TR cosine 30. And I can say, oh, this is going to be TL cosine 40. And actually, I'm going to be a little bit more precise on this and say, well, we'll call that the positive direction, and we'll call that the negative direction. You've got to have a positive and a negative direction on your line. There's no component from the 30. It's got no shadow. If you think about components as being shadows, if I have the light coming from above, this definitely has a shadow. It's definitely got a component. That one, not so much. Now it's got no shadow, no component. Now it's got a big shadow. So visualize it like that. I say the sum of the forces horizontally is equal to 0. Why do I know it's 0? Because the traffic light doesn't accelerate. It's by definition, it doesn't accelerate. So I know from context, it doesn't accelerate. So then I say, well, that means that TR cosine 30 added to minus TL cosine 30 is equal to 0. Oh, 40. Sorry, yeah, I'm tired, so watch me tonight because I'm a bit tired. Okay.
Could you also just do the different angle like all the way from 0 and not make it a negative?
So you could call it 100, 220. Is that right?
I
No.
think it's 150.
That's 90.
Yeah,
And then 50 is 140. So you could call it 140, yeah, cosine 140. I don't. I think that gets messy when the diagrams get messy, but you could. Eventually, I want to find TL. I know I'm going to do simultaneous equations. Oh, let's just let it play out. I'll come back to that. Change ink color. I'm going to go to dark green. I know there's a component there. And I even know that that's TR sine 30. And I know there's a component here. And I know that that's TL sine 40. And I know that's its own component. So that's 30. Can you see how different colored pens really divide things up? It really makes it, you're not going to mix your purples with your greens if you've trimmed them in purples and greens. But if you've done them all in black pencil or black ink, they're just numbers on a page. So I really do like different colored pens, and I'm going to say the sum of the forces vertically equals 0. It's not accelerating up or down either. So then we say, oh, I've got to do plus is upwards, down is minus. I'm going to say plus TL sine 40 added to plus TR sine 30 added to minus 30 is equal to 0. Oh, let's just try and solve it. So we say, well, I want TL. So TL is equal to, take the 30 to the other side, take the minus TR sine 30 to the other side, and divide everything by sine 40. Oh man, I don't know what TR is. Oh, hold on. Now we're going to do a bit of math. Let's go back up here. TR is equal to TL cosine 40 over cosine 30. Just substitute in. Okay. TL is equal to 30 minus, oh man, I wish I'd not rearranged. Oh well, I was trying a new way of doing it, and a more simplistic way of doing it, but it turned out it was too simplistic. I'll sort it out. Cosine 40 over cosine 30 divided by cosine, divided by sine 40. Oh, I also missed a bit. Shame on me. Yeah. I'm going to have to pause a bit and explain this. So I'm just substituting for this TR, and up here I said TR equals TL cosine 40 over cosine 30. I've got to still multiply it by sine 30 and divide it by sine 40. And it just works out that I was being too clever by half, so I've actually, this is making a lot of work for myself, but I'll just work it out. TL, bring the sine 40 back. And then bring this other stuff back here. So that's plus TL cosine 40 over cosine 30 sine 30. And that all equals 30. So I'm back up here. It's like that plus that. So it's like this line again back here. And what I did was I just substituted that in to there. So that rearrangement I did was a total waste of time. Okay. In fact, to show it's a total waste of time, I'm going to just do that. You know, it was a total waste of time. I was being too clever. So you simply take that TL cosine 40 over cosine 30, and you substitute it in. Now, I don't know what you feel about that. These are just numbers to me. Cosine, oh man, I didn't bring my calculator. Oh, so I need some help today. So what is sine 40?
.64.
0.64.
Yep.
Is that it? Okay. Plus TL. What's cosine 40?
0.77.
Multiply that by sine 30.
0.38.
And then divide all that by cosine 30.
0.44.
Add those two together. I can do that. That's going to be 1.08 TL is equal to 30. So TL is equal to 30 over 1 point. Am I right? 1.08 is right? 4 and 4 makes 8. 4 and that makes 10. Yeah. And what does that equal? What's 30 divided by 1.08?
27.72.
Sorry?
27.72.
27.7 newtons. And 27.65. I think I ran a few more decimal places, but the sines and the cosines are just fractional numbers. They're just between 0 and 1. Don't think of them. You're not going to be asked, you're not going to suddenly recognize this weird trig function that you saw at the back of your book once and the teacher knows like it's his second cousin and you have no idea. It's not going to happen. It's just a number that's between 0 and 1. So some people leave them in, some people get rid of them as soon as they can, but try and give me, I'd say 3 to 4 decimal places, and they get the same answer as me. But that's how you do them. Okay. So when I came to the States, I was driving with my buddy from New York to Boston, and we're on the interstate. 95, I guess, goes up there, and we're in the middle lane. And you don't normally in Britain stay in the middle lane because we have lane discipline, so you're always on the slow lane. But it was busy traffic, so I said, oh man, this is busy traffic. It's always like this. And then he said, just watch for a while. And the first thing I noticed was people don't indicate. And in Britain, if you don't indicate, when I was there, they'd pull you over. You didn't indicate, you're going to get a ticket. You indicate. You indicate even when you're pulling into your own driveway. You indicate, you know. So that was the first thing I noticed. And the second thing I noticed was people were passing us on both sides. And drivers would stop and shout at you if you passed them on the slow side. You're just not supposed to pass them on the slow side. It's like, it's the slow side. You want to go around me, go behind me, go on the fast side, and then go back again, you know. That's how accidents happen. You don't pass on the slow side. So I was going, this is crazy. And it's a bit like that with this, okay? You've got to have discipline. And the discipline is you've got to train yourself that you're only going to look in one axis at one time. You're not going to mix something going up there with something going up there with something. You only think in terms of one axis at one time. I don't particularly care what these axes are, but you're going to think in terms of one axis at one time. And if one axis doesn't give it, you go at 90 degrees to it and get a second axis. We're going to do that over and over again. So I thought in terms of my horizontal axis, I used my components. Notice now component is not the question. That's just the way you do it. It's just you got to know them. And I realized there was no acceleration horizontally, so I said the sum of the forces horizontal equals 0. And then that didn't give me the answer, so then I thought vertically, and I said, well, these are my components vertically, and the sum of those components equals 0 because there's no acceleration vertically. And then I kind of scratched my head. The rest is math. The rest is sums. It's like, oh, well, I got two unknowns. Just combine them together. But the physics bit, the important bit, the fundamental bit is the physics bit, and that is only using one axis at one time. Okay? And that's a real, to my mind, that's a long way doing that. I'm going to do it again. I'm going to show you a quick way of doing it. Okay? It's going to take me a while to erase it. That's the problem. There's no lasso tool where I can just get rid of it all at once, I don't think. And none of this stuff's going to stay the same, so I might as well just start again. Because the problem I've got is I've got two equations. I've got two unknowns, and so I need two equations. But wouldn't it be nice if I could just get that down to one unknown, and then I wouldn't need two equations? And that's what I'm going to do now. So again, I'm going to draw. And this is where your diagram has to be good. And this is 30. And that is t right. And that's 30. And then this is 40. It's just below the 45. And that's 40. And that's t left. Now, I want to pick an axis where t right has no component. You don't have any component when you're at 90 degrees to something. Imagine me pulling on this rod, this bar here. When I pull at an angle to the bar, there is a component. I would slide this thing. If I pull in this direction, I slide the thing. I'm not pulling it like that. I'm pulling it towards me, and can you see how it's sliding? Yeah? But if I pull here, it's not sliding. There's no component of this force in either one of those directions. So if you want to not have a component, go to 90 degrees. So then all I do is I say, oh, okay then. I don't want TR. So let's change our colored pen. I don't want TR. Let's go to purple. So I want to be at 90 degrees to TR. If that's 30 round, that's 30 round. So again, being careful to draw a good axis. By the way, axes don't have arrowheads, but forces do. So you must be doing arrowheads on some things and not arrowheads on the others. And that's going to be 30, because that's 90. Agreed? Yep. Oh. So now I simply say, well, this is actually not so bad, because I simply say, oh yeah, there's that component, there's that component, and that TR has no component. Got to work out some angles here. If that's 30 and that's 40, what's this angle in between? 20. And if that's a straight line and that's a straight line and the angle between them is 30, what's this angle down here? If that's a straight line and that's a straight line and the angle between those two straight lines is 30 degrees there, what's the angle down here? 30, yeah. What's that called? It's something complementary or similar or something. Okay. The sum of the forces, what we're going to call this? We'll call it purple line is equal to 0. This is going to be TL cosine 20. Can you see how I want the green arrow, I've got the red arrow, and I am using the angle in between, so it's cosine of that 20 degrees. And down here, this guy is going to be 30 cosine 30. Because I want the green, I got the red, and I'm using the angle in between. Now, we're going to call that positive. Why? Just because we got one of them's got to be positive and one of them's got to be negative because we're in opposite directions. I'm only looking at the green now. So call one positive, call one negative. Doesn't matter which one, as long as one is positive, one is negative. Then you say, okay, plus TL cosine 20 added to minus, this must be minus 30 cosine 30 equals 0. So TL is equal to 30 cosine 30 over cosine 20. And that equals, so what is 30 cosine 30 divided by cosine 20? So, you know, mass of writing on the previous page, even with a couple of crossings out. Next to no writing on this page. Solved it in one step, needed 2 steps. I need some geometry here. I've got to be able to play with those angles. Can you see how a bad diagram here would kill you? It's like it's not going to work well. But so don't do a bad diagram. It's like, so show of hands. How many people, their gut feeling is they prefer the first way I showed you? How many people prefer the second way? Yeah. The smart money, I hate to say it, the smart money's on the second way. Throughout this course, we're going to basically try to pick rotation axes when we're doing torque, or linear axes like we're doing now with forces that simplify the problem. It's not that you can't do them the other way, it's just that the math gets like involved. But with just by choosing a better axis, I have a much more straightforward outcome. So on a test, it would say, using a method of trigonometry, find t left or t right, and you'd show me one or the other. Yeah, cool. The reason why I'd say using a method of trigonometry is everybody okay on this? Can I start erasing? I want to show you the third way. Because there's another way, which is not better. It's different, and in some ways I think it's better. In some ways it's not as precise. I'll tell you that much. And I'm going to have to do it kind of sketchily, but you could take a pen and ink and you could do it. And that is this. These three vectors have been added together. It says the sum of the forces. They're adding vectors together. I can do that using a vector diagram when I think about it. Draw a line 30 units long. I know it's vertical because weight acts downwards. I don't know how long t right is, but I know it goes 30 degrees above the horizontal towards the right. So get your protractor and measure 30 degrees above the horizontal and draw it towards the right. It must lie on that line. Don't know how long it is, but it must lie on that line. You want to know what t left is? I don't know how long t left is, but I know that it's 40 degrees above the horizontal going towards the left. Well, that's like that, but yeah, just trace it back. So it's basically, rather than 40 degrees above, rather than doing that, just continue the line downwards. And what you find is if that's 40, that's 40. Yeah. That must be the length of my t right, and that must be the length of my t left. And if you draw that to scale, you'll get quite a decent answer out of it. Just a quite decent answer. It's quick. It's very direct. It's simple. It's not as precise. That's the only thing. Unfortunately, some people get to really like it. So I had one test where I didn't turn around and say you couldn't use that, and they would use it for everything. And part of me was really happy, and the other half was like, man, I don't even know if they know trig, you know. So I'll say, you know, using trig or using that. And I do like this, so I expect if I can fit them in one of each. Not for this test, but for the next test. But it's very nice. I had, so I've been very fortunate with my math exposure in this place, because there was one time when Professor Henderson came in and asked me a physicsy type question that I just hit on the answer straight away, and it looked so easy, you know. And you could see he was like, whoa, that's... And if he'd asked me, like, any other question, it would have been like, you know, man, but it was just one of those nice things. So he thought, I got a good reputation with him. And then there was another time when there was some of my students came in from, they were at I think the Brandon campus, and they had a teacher there in math who was giving them some problems that were sort of somewhat similar to this. There were kinetic problems, but there were. And this one was a bear, because it was like different things were unknown. And yet if you drew it out, there was this one thing where you didn't know the direction that somebody had gone in, but you knew how far they'd traveled. So it was almost like, you know, you started from here and you went to there, and then somebody else was going on that track, and you didn't know where they met, but you knew they met at such and such a time or something. So I was able to convert that into a well, that's how far I can go in that amount of time, so the answer's either that or the answer's there. And it just falls out. It's just so direct. And yet if you try to do that using, you know, algebra, it's a really long drawn out problem, and yet just graphically it falls out. So what I'm saying is, don't underestimate the power of just graphical analysis. It's really valuable. And, you know, why do a whole page of math when you can actually get an approximate answer just by drawing a few things, getting a compass and drawing some things? It makes life much easier. And you might want to go back afterwards and do the math, but you have an idea of what the answer should be. So whatever you can do. You know, this, you just basically, you want t left, you just measure it. You know, see how long it is, how many centimeters is it, convert that into newtons. Just a vector diagram. Cool. I'm going to miss this one out because I want to continue with this idea, and we'll come back in a next class basically, and we'll do some dynamics, but I want to continue with the statics for a while. Let's just stop